car's petrol tank holds 50.0 kilograms of petrol. Calculate the volume of carbon dioxide produced at a temperature of 30.0 degrees and an atmospheric pressure of 743 millimeters mercury according to the below equation. Assume the fuel is 100% octane, which is this one here, and it burns completely to produce only carbon dioxide and water as byproducts. Okay, so again, let's go through our question. A typical car's petrol tank holds 50 kilograms of petrol. Our petrol is our octane. So our mass of octane is 50.0 kilograms. I would immediately change that into grams just so you don't get stuck trying to do your calculations in kilograms. So that's actually 50,000 grams. Okay, calculate the volume of carbon dioxide. That's what we want to know. So V equals question mark. Produced at a temperature of 30 degrees. So our temperature of 30 degrees Celsius. Again, I would immediately change that into Kelvin because we don't want to get caught using degrees Celsius. So 30 degrees in Kelvin is 303 Kelvin. At an atmospheric pressure of 743 millimeters mercury. This one's a little bit trickier. So that's our pressure, P. Okay, 743 millimeters mercury. Okay, so we're going to convert this straight away again. We want to get into kilopascals for this because when we use PV equals nRT, we need it in kilopascals. So we need to go via atmospheres. And what I'll show you on our nifty Unit 1 and 2 formula sheet, if I flip over here, okay, I have a little conversion chart. So we are here and we want to get to here. So from millimeters mercury, we have to go through atmospheres. So from millimeters mercury, to get to atmospheres, we have to divide by 760. And that's because in every 1 atmosphere, we have 760 millimeters mercury. So that would end up giving us, if you put that in a calculator, actually no, we'll just go straight through because you can do this in 2 steps. We're going to do it in 1. Then to get to kilopascals, we have to multiply by 101.3. And in here, it says 101.325, but that's for, it's just a more accurate one. Definitely use the number that is in the data book, which is 101.3. So 743 divided by 760 times by 101.3 gives us a pressure of 99.03 kilopascals. Okay, I'll get rid of that one. Where are we up to? We've done our 743 millimeters mercury. Assume the fuel is 100% octane, so we're not dealing with an impure octane. Octane can come in different purities, like, you know, when you go to the petrol station, it's 91% or unleaded 95. Okay, they're percentages. But just assume that it's 100% octane and it burns completely to produce only carbon dioxide and water as byproducts because, as we know, sometimes a car can give off a black smoke, which is solid carbon. So it's saying pretend that doesn't happen. So, a stoichiometry question, we need to go through number of moles. Okay, so number of moles equals mass over molar mass equals 50,000. That's why we've completely changed this over to grams rather than kilograms. That's quite often a very easy mistake to make, and make it right at the start, which is not ideal. Divided by our molar mass, which we haven't calculated yet. So let's quickly do that. We've got let's do it down the bottom here, molar mass, we've got 8 carbons, so 8 times 12 plus 18 hydrogens, which are each 1. So that's going to be 114, my bad, grams per mole. Okay, so 114 for our molar mass. If we put that into a calculator, we get 438.6 mole. That's a lot of moles. You don't usually get that number of moles in a calculation, but we do have 50 kilograms of our octane. All right, so now we need to go through number of moles to find out the number of moles of carbon dioxide. And in this case, I use what I term a want over got scenario. So what that means is we want to know how many moles of carbon dioxide we have. We've got our number of moles for octane. Okay, so the number of moles of carbon dioxide is equal to the number of moles of octane times want divided by got. And what I mean by want divided by got, want is 16, got is 2. So we have number of moles of octane was 438.6 moles times by our want, which is 16, divided by our got, which is 2. And if we put that into our calculator, we get 3,508.8 mole. Okay, so now we're up to ascertaining V. PV equals nRT. If you rearrange that, we get V equals nRT on P. If you have a look in your data book, you will find that the R is already given to you. Where is it? Gas constant R, 831 joules per Kelvin per mole. So we've got R already, 8.31. Let's put all our numbers into our equation. N, 3508.8 times by R, which is our 8.31, times by our T, so 303, divided by our P, 99.03. So you can see how easy that was because we've already done all the preparation before. If we throw that into our calculator, we get to an answer of 89,214.5 litres. Okay, big long-winded answer. But if we look at our initial numbers and go back and look at how many significant figures we need, we've got 3 here, 3 here, 3 here. Okay, so we've got 3 significant figures. We technically could say 89,200, okay, but a better answer is to put it into scientific notation, which is 8.92 times 10 to the 4 litres.